Okay, so we've seen that you would naively expect increasing CO2 or methane to make the world warmer. But there could be all sorts of other complicated effects of raising it that might cancel this out. So we've tried a couple of natural experiments. We've seen that over the last 50 or 60 years, temperature has risen and the CO2 has risen, just as predicted. But maybe that's a coincidence, maybe there's something else going on. We've also seen that if you look back over the last few million years, the climate has changed very drastically, and it does seem that when it was colder, CO2 was lower, and that the low CO2 was a large part of why it was colder. But again, that's in the past, it was at lower temperatures. Does it really apply in the future when temperatures are higher? Can we be sure? Well, this is where models come in. General circulation models, GCMs. The same acronym GCM is also used to describe them as global climate models. Technically they're a bit different. A general circulation model just models the atmosphere. A global climate model also factors in things like ocean circulation, ice dynamics. But GCMs in general, both words are used. How do these things work and what do they tell us? So the basic idea is to break the atmosphere and the oceans up into cells and model each cell using known physics. So the idea is to try and put in some of these complexities. We've talked about many complexities like raising CO2 might change plant growth, might change wind currents, might change the atmospheric temperature profile. So we're trying to model all these things and see when you factor them all in, can we explain what's going on? So here's the basic idea. We take the atmosphere of the world and break it into cubes, or slabs. They're not cubic shaped. There'll be a vertical grid and a horizontal grid. Now typically with the current state of the art, the grids are several tens of kilometres across. This is a bit old one, but it's about a 100-kilometre grid. They're now a bit smaller than that. They might be 50 by 50 kilometres. And they might have 30 slabs going up to the top of the atmosphere, or 15 to 30 or something, and another, it went to the ocean, another 20 or 30 going down into the depths of the sea, so you can track the atmosphere at different heights and the ocean at different depths. Now that's not perfect. I mean, each cube still might be 70 by 70 kilometres, and a lot of things can happen in a 70 by 70 kilometre region. So you can look as time has gone on how their approximation for the world has got better. Here, for example, is a model of the North Atlantic from some of the early computer models with 500-kilometre size boxes. And then as time's gone on, they've got more and more accurate. This is now 110-kilometre size cubes with the height of the mountain shown. It still means that like Ireland is like 7 squares. You're not going to explain the wind blowing down a valley or a thunderstorm over some particular part of Ireland, but they are getting better. This diagram is out of date and they're now smaller grids still. This is set by the limit of the computer. As you'll see, we're going to need to do a lot of calculations for every square, and if you have too many squares, it just means it's beyond even the world's fastest supercomputers. So what do we do in each square? Well, we have to study the physics. So we might start the square off with some starting temperature, pressure, humidity, maybe whatever it happens to be today. And then one thing we factor in is the fluid dynamics. So these are the so-called Navier-Stokes equations. What this is telling us is, okay, this cube, what's the air pressure on one side or the other? If there's a high pressure on one side, that'll push the air the other way. If it's being pushed into a smaller space, it might get compressed and gets hotter. This is basically saying law of conservation of mass. Any mass that leaves one cube must go into another cube, and it tells us the force balance, that the pressure pushes things around. So this gives us the motions, conserves mass and pressure balance. And then we factor in the thermodynamics. So for each cell we look at how much radiation is coming in, how much radiation is going out, how much heat is coming in through a hot air moving in, a cold air moving out, latent heat of water vapour and so on. Again, these are all well understood laws of physics, and we use them all in each cell to model heat in, heat out, and the motions of the gas. And for the thermodynamics, we'd also factor in global warming. So you remember we looked at how much radiation we'll get in or out. So we'd look at a temperature balance. This is a temperature balance diagram for the atmosphere. So you get, on average, 342 watts of incoming solar radiation. Some of it being reflected off by clouds, some of it will hit the surface, some bounces off the surface. And then you get radiation from the surface that goes up, some of which escapes into space, some of which doesn't. There's atmospheric windows, some emitted. And so you're factoring all these things in, adding up over all the different wavelengths. So it's all very complicated. That means each cell there's a lot of calculations to do.